So I'm going to present the project of my thesis, which is the application of deep learning techniques for optical navigation in solar system exploration missions, which is supervised by Professor Manuel Sanjurjo. So as a very brief introduction, the main goal of the thesis is to study the applicability of convolutional neural networks for optical relative navigation as a lightweight and robust solution, opposed to classical methods, which normally rely on landmark tracking algorithms, which are in general computationally expensive and also fail under adverse elimination conditions. So the idea in our case is to train a neural network which is capable of directly learning the nonlinear transformation between the 2D space for a grayscale image, 3D if it's a color image, 2D 6D space for the pose vector of the spacecraft. So 3 coordinates for the position vector and 3 Euler angles. Of course, there are some challenges that we need to address. So first, the CNN kind of acts like a black box. So we have some techniques for which we can analyze a bit what's happening inside, but still we need to perform extensive testing to identify possible failure cases and scenarios. Second, as it's very well known, machine learning algorithms require a lot of data. For some missions, we have actual data for some targets, but still we don't have all the data we would need for a full general solution. And this is related with the last point, which is that we want the neural network that we train to work under all possibilities of illumination conditions, orbital ranges, mission classes, and so on. So during the project, we have investigated multiple targets or mission use cases. So we started with the simplest one, which is the Comet case, with 67P, the target of Rosetta mission. And I said simple just because most of the images are very well represented by the topography of the target. You have some dust, but can be modeled easily with some type of noise models. And in general, because of the geometry of the mission, the whole target is inside the field of view of the camera, which is easier then for the network to estimate things like distance to the target, nadir angles, and other quantities. Then we move to a more complex case like Bennu, the target of OSIRIS-REx mission, which is similar to the previous one, but in this case, we needed to implement also the albedo of the target to properly represent the images, because you have some very white spots, very dark spots, which are independent of the illumination angles. So we needed to integrate that to properly represent the images. And then we move to most complex cases, which are major bodies, like first the moon, which again, it's kind of similar to the asteroid case, but now with the disadvantage that because of the geometry of the mission, normally you don't have the limb of the target in the field of view of the camera. So you have to do some other things in the training to properly estimate distance to the target of nadir angles. And then the most complex case for us, which is the Earth, which is the one I will focus today, which is similar to the moon, but we have even more challenges, like the images are dominated by the topography and the albedo, but in this case the albedo changes with the seasons because of course snow melts, water bodies changes in size and color over the months. We also have an atmosphere which causes a lot of problems for us. There's of light scattering, weather phenomena, you have clouds which are obstructing the images. So we have to model all that to properly train the networks. And again, the limb is not inside the field of view, so we need to do some tricks there. So we focus on the OPSAT mission. So this is a CubeSat which is operated by ESOC. And you may wonder that normally you don't need optical navigation in Earth observation missions because normally you're flying LEO, so you have GPS above you, which provides very accurate position estimation. And indeed, OPSAT has a GPS antenna, but it's not working. So they have a bunch of very nice images of the Earth, but they don't know where they are from. So they reached to us to see if we could adapt the network that we did for the Comet case, in this case for the Earth case. So OPSAT is flying at 500 kilometers altitude and 97 degrees inclination, so it's a downdash orbit, which means that the local mean solar time at equatorial passes, it's always around sunrise or sunset. And this has good things and bad things. The good thing is that the illumination conditions are rather constrained because of this condition of sunrise or sunset. But on the other hand, we have very long shadows, which means that we cannot represent the images only with the albedo, as it will happen for almost zero phase angle, which is very common in Earth observation missions. But we need to integrate the topography data, which makes the generation of the images much more complex. And this is actually because we don't have enough actual data for training for this mission geometry and specifically for the camera of OPSAT. What we do is we generate ourselves the training sets with synthetic images. So we take Earth data from Google Earth Engine, which has a bunch of data sets for spectral composition. And in our case, we use topography data from the Shuttle Radar Topography mission, which has global coverage at 30 meters per pixel, which we use to create this very high resolution model of the Earth's surface. And then we take Sentinel-2 data for the surface albedo, which is very nice for us because it has a repetition of 14 days, which means that we can create multiple albedo maps of the Earth from different seasons. So we can create one for winter, summer, and so on, and then integrate all that in the training sets so the network can learn these seasonal variations and still be able to estimate the position. And here on the right, you have some examples of the real images on the top row, the corresponding synthetic ones below, in this case in grayscale. And at the bottom, the histogram of the pixel value intensity, so you can see that they match quite nicely. Just for some of them, like in the fourth case, there's a clear shift in the histogram, so that's why we'll include some data augmentation effects during training to account for this. So there are some data augmentation effects that we include on rendering time, and this is because they are completely inherent to the camera characteristics, like the altitude and scale variation, the viewpoint variation for the position and the off-nadir of the camera, the illumination conditions, intensity, light scattering, as you can see in this image for the effect of the atmosphere, Gaussian noise, which is also important in these images from offset. We have some noise in the detector, and the seasonal variations. So this is exactly the same region of the north of Los Angeles on December and on summer. So you can see all the green has gone away, the white has melted. So it looks like a different region, but still is the same. So we need to include these multiple albedo maps for the network to account for this. And then we also applied some data augmentation effects during runtime, meaning that we apply this random transformation at each epoch of the training. And these maybe are a bit more abstract. So we apply zero and zoom to model optical distortions of the lens of the camera, the channel shift for this shift in the histogram that I mentioned before, and the cutout erase technique, which is those square shapes. So we remove random sections of the images, and this is to account for blockages. In the case of the Earth, mainly because of clouds. So in this way, when a part of the image is obstructed, the network can still estimate the position, but also applies for when you have missions with some component of the spacecraft is also blocking the images. And we found actually that these three effects were key to fill the gap between synthetic and real images at different time. So once we have the images and our training techniques, we focus on the neural network architecture. So we started with a very simple one based on AlexNet, just a couple of convolution and triple connected layers. So this is very handy to fast training and analyze the trends in the different effects on the performance of the network. And then once we knew that, we moved to more complex state-of-the-art architectures. We found that BGG19, specifically a version that we modified, increasing the kernel size, provide the best performance. So for the training, we're using data sets of 200,000 images, and we achieve convergence after 500 epochs. So meaning that our training time is now about 2 days with a quite powerful GPU. But in general, we don't have overfitting, and we also apply quantization of our training because we are quantizing the network because we want to reduce the size as much as possible since we want to uplink it to the spacecraft. But actually, this quantization of our training improves the validation loss because the noise in the weights acts as a regularizing agent, so that's good for us. And in the end, we are validating the networks with real images from offset, which again have never been seen before by the network, which are only trained on synthetic images. And we found none or very little degradation on the accuracy when estimating the position for real images. On the right, you see some examples of the synthetic image and the corresponding real one and the estimation of the latitude and longitude for those images with the network. And we have also tested the network in the same motherboard that it's on board OPSAT, the ARM64 with 8 GB RAM. We are achieving a data rate of about 12 frames per second. So we can implement that with a filter, which actually improves a lot the position estimation. And the total size of the network is less than 20 megabytes, meaning that we can uplink the whole model in a single ground pass. So hopefully very soon we'll be able to test it in orbit in offset. And also there's a CubeSat from Firefly, which it's also interested in testing this one and the one that we train for the moon in the future, hopefully. So last on achievements, we have published a couple of papers. One on the Comet case, that was the first one that we published one few months ago on the Earth case. And we have an abstract accepted for the International Astronautical Congress in Milano this year, in which we'll present the results for the lunar case, for which we have also implemented descent and landing on the lunar south pole, which has very challenging illumination conditions. So that's it. Here you have the QR codes for the papers in case you want to take a look, and I would be happy to take questions. Thank you.